so the first question on this exam review is finding the pH of a weak acid. Okay, phenol is a weak acid. It has a Ka 1 times 10 to the minus 10. So when you're given a problem like this, any weak acid, okay, this is the weak acid on the this is the weak acid for this example. On your test, your actual test on Monday, you'll have another weak acid. Okay, not this one, but just a similar weak acid. You're going to go through the same steps that I'm about to go through. So the first thing is you want to write the equation. Okay, for the Ka. I'm going to try to go fast to cover more of the exam, or as much of the exam as I can here. Alright, so the Ka, this weak acid delivers a proton, as we learned in chapter 15, and it will give you the hydromonium ion. Let me put the states in here. Aqueous water will always be a liquid, and that's aqueous. Okay. And then you're going to get the conjugate. So that's the first thing, and this has a Ka of 1 times 10 to the minus 10. All right, so we'll do our ice table. Okay, the starting concentration is 0.025. Okay, this is the Ka. And so we don't care about the liquids. Okay, ICE. So we have 0.025. This will be 0, this will be 0. So if you actually have a bottle of phenolic acid, I think we have one in our lab, it's not only phenolic acid in that bottle. You'll have some small proportion of hydromonium ion and some small proportion of this conjugate base. So it's going to be minus x plus x plus x. And at equilibrium, you'll have some formation of H3O plus, and you'll have some formation of CH6H5O minus. So we'll plug that into the to the equilibrium expression. So do you guys remember this for the exam? Ka is equal to products over reactants. Okay, we'll plug in our numbers. Ka is 1.00 times 10 to the minus 10. I'll give you the Ka for this, for whatever weak acid on the exam. You'll get a different acid, okay, but you'll do the exact same math. H3O is x, C6H5O minus is x times x is x squared, and C6H5OH is 0.025 minus x. You can go ahead and assume that x is small, so that 0.025 minus x is about 0.025. Okay, so 1.00 times 10 to the minus 10 equals x squared divided by 0.025. Alright, so 1.00 times 10 to the minus 10 times 0.025. Okay, I'm going to go square root that to get us x, from x squared to get x. And what is this, 2.5 times 10 to the minus 8? Let me see how. Oh, 10 to the minus 12, I'm sorry, I'm backwards. Okay, 2.5 times 10 to the minus 12. And I'm going to square root that to give us x. So square rooting this, I mean 1.58 times 1, 2, 3, 4, 10 to the minus 6. Okay, this is molar. Okay, so what does that x really symbolize? Okay, this x really is this x, which is the concentration of H3O plus. All right, so we can do pH is equal to minus the log of the H3O plus concentration. Okay, this is our definition of pH. Okay, pH is minus the log of our X, which is 1.58 times 10 to the minus 6. 1.58 times 10 to the minus 6. And what is this on our calculator? 5.8. I have another digit, 5.86, 5.8. 5.80, okay. And this is our answer. Okay, our pH is equal to 5.80. All right, so very similar to on the exam, but on the exam you won't be given phenolic acid. You'll get a different weak acid with a different Ka. Okay, is that okay? All right, you'll do the exact same thing. Okay, I think on the exam it's going to be boric acid. I think on the exam, I do not know, but it's this. So one of the protons leaves. Okay, even though it's triproduct, one of them leaves and goes through this. So you do the exact same thing. All right, are there any questions on this? All right, so make sure you know how to do that. And you can use the low ionization assumption. Okay, that is assuming X is small. All right, shall we move on to another problem here? All right, let's move on to page 2 here. Okay, in our first problem we had pH of phenolic acid. Now we have a pH of 0.25 molar HCl. Okay, should we use an ice table here? Yes or no? Okay, so HCl is what is called a strong acid. Okay, so can anyone name to me those 6 strong acids here? Okay, one of them is HCl. One is HNO3. What's another one? Okay, HI, HBr. One that we don't see a lot, but it's also strong, perchloric acid. And the first one. Okay, it's a diproduct, but one of them, the first one, is acidic. So these are our 6 strong acids. So if you immediately have them memorized and you immediately see them, you don't have to use an ice table. Okay, what can you do? Okay, you can plug it in straight to the pH equation because it's a strong acid. So we say generally it's 100% or close to 100% H plus. Okay. So what is minus the log of 0.25? 0.602. That's correct. Okay. Does pH have units? Somebody's lab report, I remember, they're all good and they're all nice and stuff, but they had a lab report where the pH had units of molar. Okay. So don't do that. Okay. pH has no units. It's a scale, and a scale doesn't have units. So this one is pretty straightforward, right? You plug it into the pH equation because it's a strong acid. You plug the concentration in. Yeah. All right. What about lithium hydroxide? What do you think that is? Is this a weak base that needs a Kb? Yes or no? Okay, what are strong bases? Okay, anything that has that OH is a strong base. Okay, anything that has that OH minus is a strong base. So this is actually lithium ion and hydroxide ion. So instead of calculating pH, what should we calculate first? POH. Okay, we'll calculate POH first. That is correct. So we'll calculate POH and then from there get pH. Okay, minus the log. So you can plug that in straight in here because it's a strong base, a good source of hydroxide ion. Okay, so what do you guys do when you plug that into your calculator? 0.903. Okay, is this your answer? Okay, so we got our POH, and now let's get our pH. And our pH is going to be 14 minus 0.903. And that is 13.10, I guess. If you round, it'll be 13.10. So that's a very basic pH. Okay. You have to remember this is a scale. There's no units. And 7 is considered neutral, where the concentration of H plus equals the concentration of OH minus. Okay. Yeah, it's actually 1.00 times 10 to the minus 7 molar. Okay, once you get above that scale, the pH becomes basic. 13 is very basic. And then once it gets below that scale, it's acidic. And generally, the scale runs from 0 to 14. So this problem is just making you realize that if it's strong acid, you plug it into the pH equation. If it's a strong base, you can plug it into the POH equation and then use this to get the pH. Okay, remember the relationship pH plus POH is equal to 14. Okay. Same situation here with question 3. On this exam, the POH of a solution is 11. Show your work for full credit. Calculate the pH of the solution. Okay. Should this be easy? What will the pH be? 3. Very good. Okay. What is the hydrogen ion concentration for something that registers a pH of 3? Okay, so we're going to do the back calculation for this, the back end. Okay, so the concentration H3O plus is going to be anti-log, or the shift log on your calculator, 10 to the power of minus pH. Okay, and the pH here is 3, so it's 10 to the power of minus 3. And what is that on our calculator? 0.003, I think. Okay, so look here, I'm doing not log, but the shift log, shift log, minus 3, which is minus the pH, and 0.001. Okay, do I need units here? Okay, the answer is yes, I will need units, and the units are going to be in moles over liter. So where students get mistakes is they don't put the units. Okay, pH is unitless, but the concentration that registered that pH in the pH meter has units of concentration, moles over liter, molar. Okay, once again, pH is no units. Okay, but the concentration of the hydrogen ion that gives us this pH meter reading is in molarity, moles over liter. And let's complete C and D here. I'll answer part D. Okay, is this solution basic, acidic, or neutral? What do you think it would be with a pH of 3? Acidic? Okay, it's definitely going to be acidic. Okay. And what is the hydroxide ion concentration at this pH? Okay. Well, if the hydrogen ion concentration is 0.001, what is the hydroxide ion concentration? What will it be? Anybody know the equation for that? Okay, that's one way. Actually, that's a good one. I wasn't even thinking about that. So our pOH is going to be 11, okay, because pH plus pOH is equal to 14. So OH minus is going to be 10 to the power of minus pOH, which equals 10 to the power of minus 11. And on our calculator, that is 1 times 10 to the minus 11 molar. Okay, so you're going to do shift log or second log power of minus pOH, which is minus 11. And that's 1 times 10 to the minus 11. Okay. We're going to put in here units of molarity. Okay, units of molar. So that's a good one, Michael. You can calculate pOH and then do this back calculation to get the concentration. I was actually, in my mind, I was going to teach you guys this. Okay, the concentration of H plus times the concentration of OH minus is equal to KW. And KW was given to us here as 1 times 10 to the minus 14. Okay, I was going to use this equation. You can use that equation and solve for OH minus. And which we found in part B that H plus concentration is this. Okay, so that's another way you can do this exact same problem. Or you can do Michael's way as well, which is also good. All right, are there any questions on this? All right, so those are the types of acid-base problems you'll see on the exam. Oh, come on, come on, come on. All right, any questions or comments? So, yeah. So, something very similar on the test, maybe just a little different numbers, that's all. But the basic idea, the basic strategy is going to be the same. All right, write the chemical equation Kb for bicarbonate. Okay, so here we're not talking about Ka, but we're talking about Kb. Okay? All right, so what is a Kb equation? Okay, it starts off with a weak base. Okay. Don't forget the state is water. And what is it reacting with? For a Kb, it's the same it reacts with for a Ka. But what will it react with? So this is the weak base. I'll just call it base. Okay, what will it react with in the Kb? Water. Okay. Okay, so here, unlike the Ka reaction, in the Kb reaction, water is the acid. Water can be both an acid or a base. And what do bases do? Okay, Brunstad bases take protons. Okay, so Brunstad base will take protons, and when it does, this H2O that gives off the proton becomes OH minus. Okay, and this HCO3 minus bicarb or bicarbonate picks up that proton and it becomes H2CO3. And yeah, that's it for this type of problem. Okay, so this is what you want to know. Okay, given now on your exam you won't be given this weak base but another type of weak base. Okay, so all KBs will give you OH minus because it's a source of base, so hence KB, and this is going to be the conjugate base. Okay, so these two are a pair, and HCO3 minus has its conjugate acid, and what is its conjugate acid? Okay, it's H2CO3. So that's a pretty straightforward problem. Right? So on the exam you'll be given a similar weak base. You just have to follow this. Okay, make sure you have the correct conjugate acid for this conjugate base. Okay, what's the total charge on the product side? Product side. What's the total charge? -1. What's the total charge on the reactant side? Total charge? -1 as well. So is this balanced in charge? Yes. Okay, -1 here on reactant side and -1 here on the product side. So we are balanced in charge, and we should be balanced as an equation. And I believe we are. A quick check tells me that yes, we are balanced. Okay. So make sure you are charge balanced as well as atom balanced. Okay. Any questions on this? Okay, so similar type of problem. Okay, you'll be given, so if you see a KB here, you automatically know that whatever chemical I'm putting in there is going to be a weak base. Okay, the minute you say KB, okay, you should realize that that is weak base that I'm writing in there, that you have to write the equation for. Okay, what is the Ka for this acid, carbonic acid? So this is the Kb equation. Okay, what if they ask you for the Ka? Okay, so this base reacts with water to give you this. This acid reacts with water to give you the Ka for this reaction. Okay, so here water is acting like a base and abstracting this proton from an acid, and acids love to give off protons. Some like to do it better than others. And you're going to get H3O plus bicarbonate. Okay, so this is the Ka. Right, so here H2O is acting like the base, and this is its conjugate acid. Carbonic acid is an acid, and all acids do is give off protons, but some do it better than others, especially the strong acids, those 6 strong acids. So this is the acid, and this is its conjugate base. Okay. So I mean, on the exam it's Kb, but this would be the thing if it asks for Ka. Okay. And just to complete this, if you add these two up, you actually get Kw. Okay, if you were to add this and this, if you add 2 equilibrium reactions, you multiply the constants. Ka times Kb is Kw. And then this cancels out with this cancels out with that, and you're left with 2H2O. It's actually doing acid base on itself, OH minus plus H3O plus. Okay, So that's why Ka is equal to, that's why Ka times Kb is equal to Kw. All right, so let's move on here to the next part of this exam. All right, ranking acids. Okay. All right, the key to solving this problem is this. The key to solving this problem is that the higher the Ka, okay, the more the reaction moves forward. But because of the minus log, it's the lower the pKa. Okay, this metric. Higher the Ka corresponds to lower pKa. This is the guide to tell us how strong an acid is. Such that if you have a very high Ka, this means it has a very low pKa, because power of Ka, pKa is minus the log of Ka. I think that's just because of the math of the log, and that just means a stronger acid. So in this particular problem, what I would do is I would quickly calculate the pKa by doing minus the log. So let's do that really fast. Minus the log of 7.2 times 10 to the minus 4. Okay, 3.14. Okay, minus the log of 1.9 times 10 to the minus 5 for HN3. 1, 2, 3, 4. Uh, 4.72. Okay, iodic acid, I believe that's called, minus the log of 0.16, 0.7 or 0.80, minus the log of 3.5 times 10 to the minus 8. 7.46. Okay, minus the log of 6.2 times 10 to the minus 10. 9.21. Okay, just doing minus the log of the Kas. Finally, minus the log of 4.0 times 10 to the minus 4. 3.40. Okay, make sure I got those numbers right. Okay, now we're at a situation where we can rank these based upon the Kas or the pKa. So what does it say here? Least acidic to most acidic. Least acidic to most acidic. So the most acidic would have the lowest, right? Lowest pKa, highest Ka. Most acidic. So what is the lowest pKa here? HiO3. So I'm going to label that 1, 2, 3, 4. I'm going to label that 6. 6, okay? What would be the least acidic? Which one would have the highest pKa? 9.21. Okay? Yeah? What's this? What's this spam? Which one again, Michael? Sorry.
HiO3 isn't that the highest Ka? 0.16 is bigger than all the other Kas.
Right, so it would be the strongest acid. So it would be the most acidic. Right? Most acidic would be number 6. Least acidic would be number 1. Yeah, that's also tricky.
Yeah.
Okay.
I'll list them,
Okay, you can do that too. That's fine. But when I grade it, probably most acidic is that. Least acidic is 10 to the minus 10. Okay, what's the next least acidic? 10 to the minus 8, is that correct? Okay, what's the next least acidic? 10 to the minus 5, right? Just double check me. And then what is the next least acidic? It should be HNO2, right? pK 3.40. The lower the pKa, the stronger the acid. So yeah, the lower the pKa, the stronger the acid. So yeah. The lower the pKa, the stronger the acid. So this would be the most acidic. And then this would be the next most acidic. Anyways, you can, yeah, that's how you do it. This is what you're going to go by. All right. This is definitely the strongest acid because it has the highest Ka. And this is definitely the weakest acid because it has the lowest Ka. So then you're going to rank everything accordingly. So this is the lowest. What's the next lowest? What's the next lowest? 10 to the minus 10. 10 to the minus 8. And then what's the next lowest? 10 to the minus 5. And then what's the next lowest? 4. And then what's the next lowest? 5. And then the highest, obviously, is that. Okay, lowest. Okay, lowest or the highest. Yeah, you're going to go for the lowest. Yeah. So in other words, it's this. Okay, if you have a high Ka, okay, and this is the highest amongst the list. Low Ka, okay, we're talking about a strong acid to a weak acid. All right. I got this from a textbook, and that's a tough textbook, okay? Make sure you don't get your numbers confused, especially if you think backwards like I do. Okay? All right. All right, are there any questions on this? The only thing you need to just clarify in your mind is that the highest Ka will be the strongest acid, so that is the most acidic. Okay. The lowest Ka will be the weakest acid, and that's the least acidic. Okay, then everything goes by chronology there. All right, so that is on the exam. Okay. All right, in the last 10 minutes or so, 15 minutes, let's do a titration problem here. All right, so calculate the pH of a solution by adding 35 mL of 0.1 molar formic acid with 30 mL of 0.1 molar NaOH. So this would be the strong base. This would be the weak acid. Just, I was searching my notebook here. The Ka for formic acid is 1.8 times 10 to the minus 4. So I'll give you that on the exam. So, okay, so I'll give you that Ka for formic acid. I'll give you all the Kas. Okay, if I forget the Ka, I'll throw out that problem. But okay, I'm going to make sure I'll put all the Kas in. All right, so this is what happens when this weak acid reacts with this strong base. Okay, it's not reacting with water, it's reacting with the strong base. Okay, the sodium ion is not doing anything. Okay, it's not doing anything, it's not reacting. Okay, so it's going to grab very, very strongly that proton from this weak acid because it's a strong base, and this will give you H2O liquid plus formate ion. Okay. No, you don't have to. because the sodium ion doesn't do anything. It's not participating in any acid-base reaction. The sodium ion does absolutely nothing to the pH or POH. Yeah, okay. It does not take a proton. It does not release a proton. All right, so we're going to calculate the concentrations after mixing. All right, so we have, we'll first do formic acid. And that is, we're taking 35 mLs of a 0.1 molar. What's the total volume after we add this to the base? 65 mLs. Okay, so 35 times 0.1 is 3.5. That I know. Divided by 65. 0.0538 big M. Alright, so that is our formic acid concentration after we mix these two substances together. Okay, and now we'll do the NaOH concentration, or the OH concentration, after mixing. (30 mLs times 0.1 molar divided by 65 mLs, and 30 times 0.1 is 3, divided by 65, and that's 0.0462 molar. So on one end we have 0.0538 molar. On the other end, after mixing all them up, the total concentration, or the final concentration, will be 0.0462 molar. Okay, we don't care about the liquid. And then how much of this OH will eat up this formic acid? Okay, it's going to eat up all of it. Okay. All of it. Okay. Eat up all of it until it's all gone. So all the OH is gone. Here we have 0.0538 minus 0.0462 and 0.0076. This is 0.0462 big M. Alright, so we got a little bit of the acid, we have a little bit of the conjugate base, so we'll use the Henderson-Hasselbalch equation. So I'll give you that Henderson-Hasselbalch equation on the exam. So pH is equal to pKa plus the log of, you drop the acid, and on the numerator you have the base. Okay, pKa is minus the log of Ka. Plus log of HCOOH is 0.0076. And then that's 0.0462. And this is the answer after you put it in your calculator. So what is that on our calculator here? So I'm going to do minus the log of 1.8 times 10 to the minus 4. And that's 3.74. Plus, so you're going to do this fraction first, 0.00462 divided by 0.0076. Sorry, 0.0462 divided by 0.0076. Log that, 0.78 plus 3.74. I'm getting about 4.52. Anybody else got that on their calculator? Okay, I got one person who got that, which means I'm pretty confident the answer is correct. All I need is one person. Okay. 4.52, and this is the answer. All right, so I'll give you this equation on the exam. Okay, this is called the Henderson-Hasselbalch equation. You'll only use that equation if you have some of the acid left over with some of the conjugate base. If you have these two present, then that's the equation we'll use. Okay, if you have this present, you just use the pOH equation to find pH. But we don't have this present, it's all gone, because this is a strong base. It eats up all of the weak acid, but you have this left over. Okay.
So only if we have either OH or hydronium in the products do we use that, like the negative log of the concentration?
Right. Anytime you have leftover OH, you can use that. Or if you have leftover H+, you can use the negative log of the concentration. Here we can't use the negative log of the concentration. How come? Because we have this and this. This is called a buffer, by the way. You have a little bit of your acid and a little bit of your base. Yeah. What happens if this was the equivalence point? You had a 0 here, and imagine you had a 0 here. Then how would you calculate the pH? You'd use the reverse reaction. Yes, you'd use the reverse reaction. All right, we have 3 more problems left to do, so let's finish up this one here. All right, write the KSP expression for silver 1 phosphate. So, just checking the time here. Okay, write the KSP expression for silver 1 phosphate. Okay, so silver has a +1 charge. Phosphate, if you remember from Chem 1, has a -3 charge. Okay, so we do the switcheroo for ionic compounds, and we get the final formula of AgPO4. Okay, so it's asking for KSP. So anytime you see KSP, okay, we are going to take the solid and break it down into its ions. Okay, take the solid and break it down into its ions. So that's going to be this will break down into Ag plus PO4 -3 aqueous. Okay, we want to balance this. Balance it. Okay, so that's one part of this answer. Okay. What's the second part of this answer? Okay, from this KSP equation, okay, don't forget to balance it and don't forget the states. And then from the second part of this equation, we'll actually do the KSP expression. Okay, it's products over reactants. Okay, products over reactants. So this is a solid, so we don't do anything with that. It's going to be Ag plus cubed times PO4 -3. Okay. And these are the two correct, these are both what you want to give for this answer. So where students make mistakes is not balancing this KSP, not putting the correct states, solid and aqueous, and then not writing this equation. Okay, it's products over reactants. Okay, why did we not put any reactants here in the denominator? It's a solid, so solids have a concentration, but solids don't have a concentration, so they don't have a concentrations. They have a density, so we don't put that in there. We have 2 more problems, and that will really cover all the major aspects of this exam. Okay, so this type of problem is a common ion. Okay, it illustrates the common ion effect. Okay, so what is the solubility S of silver carbonate? So silver is going to be Ag plus, carbonate is CO3 minus 2, in the presence of sodium carbonate. So sodium is Na plus, carbonate is CO3 minus 2, and the KSP is this, 8.10 times 10 to the minus 12. So the first thing we'll do to solve this problem is we'll write the equation for the KSP here. Okay, this solid is in an equilibrium with Ag plus. Okay, plus CO3 minus 2. Okay, you want to balance this. And the KSP, like we said before, is products over reactants, so it's going to be Ag plus squared, okay, squared times CO3 minus 2. All right, some of that's going to go this way, okay, some of it's going to go this way, and when it does, this is going to be not plus S, but plus 2S, and this would be S plus the common ion. So the common ion here is 0.10 molar. Okay, so there's 2 sources of CO3 minus 2. One source of CO3 minus 2 is this solid Ag2CO3 going back this way. Okay, and this is that equilibrium constant for that. And the other source of CO3 minus 2 is the actual solvent that is being used to dissolve, and that is 0.10 molar sodium carbonate. So there are 2 sources of CO3 minus 2. So we'll plug that in here. So KSP is 8.10 times 10 to the minus 12. 2S, don't forget to square it. And then it's going to be S plus 0.10 molar. Okay, so here we'll assume S is small. Okay, so when we assume S is small, S plus 0.10 molar is about 0.10 molar. Okay, which means most of the CO3 minus 2 is coming from the common ion. Okay, some, but not a lot, is actually coming from this back reaction. Okay. So this becomes 8.10 times 10 to the minus 12 equals 4s squared, and this s plus 0.10 molar becomes 0.10. Okay. And then we'll solve for this 8.10 times 10 to the minus 12. 4 times 0.1 is 0.4. And I'm going to divide it here. And then I'm going to square root it to get to s. Four times 0.1 is 0.4, and divide it both sides by 0.4, square root it to get s, and then this should be my final answer. 8 times 10 to the negative 12 divided by 0.40, and let's square root that. Getting 4.5 or 4.47. Okay, S is equal to 4.5 times 10 to the minus 6 molar. Okay, don't forget the molar here. So the final answer, the solubility of Ag, is actually not this S, but 2 times that. So that's 9 times 10 to the minus 6 molar solubility of Ag plus, and then the solubility of carbonate is going to be S plus that, so it's going to be 4.5 times 10 to the minus 6 molar plus your 0.1 molar. Okay. And if you do 4.5 times 10 to the minus 6 plus 0.1 on your calculator, you'll probably get something like 0.1. Okay. Right. So that is a majority of the review for this exam. We have one more problem. Will the precipitate form? So this is where we'll use the Gator rule, but we'll do that on Friday, and then we'll do continue to work on chapter 17.